Hi there. Purpose of this video is to explain by experiment the resistor, capacitor, charge, discharge cycles. There is a mathematical equation for the voltage across the capacitor at any time t. V, which is the supply voltage, in this case 10, DC power supply, 1 minus Euler's number to the power of minus T over RC. RC is the time constant of the circuit. E is Euler's number. It's a constant that defines natural growth and decay, 2.7128. Natural, this is a natural process. Capacitance stores charge. For example, your body's a capacitor. We want to see if this mathematical expression can be verified by experiment. RC is a time constant. It should take us from 0 volts to 6.3 volts. That charge cycle should take 2 seconds. It should take 5 time constants to get to 99% of the supply voltage, which is 10 volts. And we want to see by experiment whether we can verify this mathematical equation. On the electronic box, 1K, 2000 microfarad, simple mechanical switch, on switch, current, voltage, digital scope. So what we're going to do now, current is 0, voltage is 0. We're going to just make sure that it is discharged properly. We can see the voltage coming down, right down to 0 volts across the capacitor. We're making sure it's fully discharged. Voltage has gone down to 0. What we're going to do now is we're going to capture rising edge. We want to capture the nonlinear voltage across the capacitor on the digital scope. So what we're going to do is to put that switch on. We can see it charging up the voltage here. We can see the current. It started at 10 milliamps and it goes down to 0 when the capacitor is fully charged. And if we have triggered the oscilloscope properly, which is on 2-second time base, we should be able to see the voltage curve. So I'll take my finger off the switch. I've now disconnected the power supply. There is a bit of a leakage through the capacitor. You can see it's dropping slightly. What we want to do now is to analyze the cursors and see if we can verify the 2 seconds. So what I'm going to do is put that cursor there, which is time 0, 0 volts. I want the other cursor, so press cursors. I want this cursor here. I want to measure it so I can move it. So what we're looking at here is we want to see 6.3 volts. So we're on 2 volts per division vertically. So 2, 4, 6. So we're just above here. So if we go to here, just the other side, for 6.3 volts. So we're on 0 volts here, 2, 4, 6, just above 6 is there. And we can see if we measure, we've got 2.12 seconds. So within reason, that does verify our mathematical expression. How long is it taking to get up to 99% of 10 volts? So we're really talking about getting up to 10 volts. We can see that the rate of change of the voltage is very steep initially, and once it gets charged up, the rate of change slows down and it takes quite a long time to get to the full value. This is a curve, an exponential curve defined by Euler's number. It's not a straight line, it's not linear. If we look at that time difference there, we can confirm it does take 10 seconds to get up to the full 10 volts. So we're going 0, 2, 4, 6, 8, 10. So that does confirm by experiment. It takes 5 time constants to get up to 99% of the supply voltage, which is 10 volts. What we want to do now is to see the discharge cycle. So what we've got now is a different circuit. What that circuit is we're just going to short out the 1K and the resistor and the capacitor with a wire. Again, we've got the same time constant, slightly different voltage equation, where it's the voltage times Eulers number. There's no 1 minus. That's because we're actually starting at 10 volts. If you think about time 0, well, any number to the power of 0 is 1. So at time 0, we're actually at the supply voltage of 10 volts, and then they will come down on an exponential curve. So what we want to do now is we want to change the trigger setup. We want the falling edge now. We want to see it coming down from 10 volts, and want to change the trigger level up there. We want to clear it. We want to put it in single shot. I just want to make sure it's fully charged up again. There does seem to be a fair bit of leakage. It's dropped. I just want to get it back up to 10 volts again, which it is now. So what we're going to do now is wire connect across R and C to discharge it. You can see the voltage is dropping rapidly. Current is now in the opposite direction. Why is that? Current is now flowing out of the capacitor through the resistor, being dissipated as heat, and eventually all the energy stored in the capacitor will be dissipated as heat coming out of the resistor. What we can see now is we've got an exponential curve coming down from 10 volts. So what we should be able to see is we should be able to see a 63% drop from 10 volts within 2 seconds. So we should be able to go down from 10 volts to 3.7 volts within 2 seconds. So if we change the cursors again, I just want to change that cursor, the original the starting cursor, measure it. Just want to move it slightly along, depending on how good your eyesight is, to there, where it would start of the discharge. To do the other cursor, I need to press that again, highlight the other cursor, measure it, move it along. So what we're looking for is down to 3.7 volts. So we're going from 10, 8, 6, 4, 2, so 3.7 is going to be about there. So we're talking, so that if the cursor was there, we'd go from 10, 8, 6, 4, so 3.7 is about there. So we're looking at about 2.4 seconds. It's a little bit more than expected, but it does verify that voltage drops very rapidly, and then it will take 10 seconds to get anywhere near down to 0 volts. So we're really talking about really down here. Yeah. That looks like, if you say that, I would say that's really taken about 12 seconds there to get down. So we have verified the time constant. Thank you for watching. Any comments, please leave below.